Suppose the Ebola epidemic is modeled by exponential growth. The rate at which the number of cases changes with time is proportional to the number of individuals already infected. For the infected individuals, dn over dt equals 0.148 n, when n is the number of infected individuals and t is measured in weeks. On March 25, 2014, the World Health Organization discovered an initial 86 cases of the disease in West Africa. Find the initial value problem that creates an exponential equation to describe the Ebola epidemic. Remember the exponential equation n of t equals n sub o e to the kt, and its derivative dn over dt equals kn, where t is time, n sub o is the initial value, n of t is the amount after time, and k is a constant. By plugging in the given values k, t, and s from the given derivative into the exponential equation, you may find your initial value. Since k equals 0.148, the number of those infected n is 86 at time 0, s sub 0 equals 86. The exponential equation to model the Ebola epidemic is n of t equals 86 times e to the 0.148 t power. How many cases of Ebola would be present in week 20? Since you already have your exponential equation n of t equals 86 e to the 0.148 t power, you may substitute the time t, 20, into your equation and solve for n of t, the number of infected present in week 20, which is 1,666 cases. Let's compare this to the actual Ebola case data from the World Health Organization. In week 20, August 8, 2014, the number of total Ebola cases was 1,766. But wait a second, these figures don't add up. Although useful in projecting the overarching trend of an epidemic, the exponential growth model can only serve as a draft prediction of a short-term growth. Due to its assumption of a constant growth rate, which also refers to the transmission rate, certain factors are excluded from the calculation, such as average contact with non-infected persons, further resulting in a given lack of applicability to real-world scenarios.